Hey everyone, and a very warm welcome to Hafee Sleep. Whether you're here to unwind after a long day, to drift off into a world of ideas, or you're just waking up and need some cosmic fuel for your thoughts, I'm so glad you found your way here. Now, before we dive deep, do me a quick favor. If the sound of unraveling the universe's greatest mysteries helps you relax or sparks your curiosity, please hit that subscribe button and give this video a like. It truly helps this channel grow and allows me to bring more of these deep dive stories to you. And because this community is so wonderfully global, I'd love to hear from you. As you're settling in, just drop a quick comment down below and tell me where in the world you're watching from and what time it is for you. Are you cozying up for a late-night thought session in London? Is it the middle of the afternoon in Sydney? Or are you, like me sometimes, just ignoring the clock entirely? Let me know. It's always fascinating to see just how far and wide our community of curious minds stretches. So, what are we unraveling tonight? We are embarking on an incredible journey into the most mind-bending, reality-questioning, and famous paradoxes in all of physics. We're talking about cats that are both here and there, twins aging at different speeds, and why the silent, dark night sky is one of the biggest clues to the universe's past. This is a full, immersive exploration where we leave no stone unturned, explaining every minute detail in the simplest, most relaxing way possible. So, get comfortable. Dim the lights if you haven't already. Let your mind relax and get ready to explore the beautiful cracks in the fabric of reality itself. Let's begin. Have you ever been lying awake at night, staring at the ceiling, and a thought strikes you so strange that it seems to break your own brain? A thought that feels like two opposite truths trying to occupy the same space in your mind? Maybe you've wondered, if the universe is infinite, why is the sky dark at night? Or how can a cat be both dead and alive at the very same time? Welcome, everyone, to the most fascinating, mind-bending, and beautifully confusing corners of science. Welcome to the world of physics paradoxes. These aren't just puzzles or tricks. They are cracks in the surface of our understanding. They are places where the universe, in its infinite wisdom, seems to look directly at us and whisper, "You don't know the whole story yet." For centuries, these paradoxes have been nagging at the greatest thinkers, from philosophers in sandals to physicists in lab coats. They have forced us to question everything we thought we knew about space, time, reality, and our place in the cosmos. And in the struggle to resolve them, we have not only found answers, but have rewritten the fundamental laws of reality itself. Our journey today will take us from ancient Greece to the precipice of black holes, from the simple act of walking to the park, to the bizarre quantum realm where logic itself takes a holiday. We will meet heroes and tortoises, twins and cats, grandfathers and lonely aliens. We will see how a simple walk across a room unravels into a confrontation with infinity. We will see how the fate of a feline hinges on the spooky rules of the quantum world. We will witness a starship captain aging slower than his earthbound brother, and we will stare into the abyss of a black hole, wondering if everything that falls in is lost forever. So, get comfortable. Open your mind. Don't worry if things seem strange at first. That's the whole point. We're about to turn reality inside out and upside down, and I promise, by the end, the universe will look a little more amazing and a lot more mysterious than it ever has before. Let's begin with one of the oldest and most deceptively simple paradoxes ever conceived. a paradox that questioned the very possibility of movement itself. Our first story comes from the sun-baked hills of ancient Greece, with a philosopher named Zeno and a heroine named Atalanta, who was just trying to go for a run. Our first stop is in ancient Greece, with a philosopher named Zeno of Elea and his famous paradoxes of motion. Zeno wasn't a scientist in the modern sense. He was a thinker, and he was trying to defend the ideas of his teacher, Parmenides, who argued that change and motion were ultimately illusions. To prove this, Zeno crafted a series of logical arguments that showed motion was, well, logically impossible. The most famous of these is the paradox of Achilles and the tortoise. Imagine the scene. The great hero Achilles, the fastest runner in all of Greece, is set to race against a slow-moving tortoise. Now, being a sporting fellow, Achilles gives the tortoise a head start of, say, 100 meters. The race begins. In a flash, Achilles covers the 100 meters to the point where the tortoise started. But in that time, the tortoise, slow as it is, has moved forward. It has moved maybe 1 meter, so Achilles now has to cover that 1 meter. He does so in an instant. But again, in that tiny instant, the tortoise has moved a little further, maybe a centimeter. So Achilles must now cover that centimeter. And by the time he does, the tortoise has moved a millimeter, and so on, and so forth. Zeno's argument was this: every time Achilles reaches the point where the tortoise was, the tortoise has always moved to a new point. There will always be some distance, however infinitesimally small, left for Achilles to cover. He must first reach the tortoise's previous position, which always creates a new, smaller gap. Since this process goes on forever, with an infinite number of these tiny gaps to cross, the swift-footed Achilles can logically never overtake the plodding tortoise. This feels wrong, doesn't it? We know from everyday experience that Achilles would blow past the tortoise without a second thought. So, what's the flaw? For the longest time, this was considered a purely philosophical and mathematical problem. The mathematical resolution came with the understanding of infinite series. An infinite sum of numbers doesn't necessarily have to be infinitely large. The series of distances Achilles must cover, 100 meters, plus 1 meter, plus 1 centimeters, plus 1 meters, and so on, is an infinite series, but it converges to a finite value. It adds up to a specific finite distance, and since Achilles runs at a finite speed, it takes him a finite amount of time to cover that total distance. At that specific point, he overtakes the tortoise. But is math enough? Some physicists would argue no, because math deals with idealized concepts. The real physical resolution is even more profound. Our universe is not infinitely divisible. We live in a quantum universe. There is a smallest possible scale known as the Planck length, below which the concepts of distance and position lose their meaning. You can't have an infinite number of steps if the universe itself doesn't allow for measurements that are infinitely small. So, in the real physical world, there comes a point where Achilles is simply closer to the tortoise than the minimum meaningful distance. He is, for all practical and physical purposes, at the same point, and in the very next instant, he passes it. Physics, not just math, finally resolves the paradox by showing us that the universe is not the continuous, infinitely divisible realm that Zeno imagined. It is grainy, it is quantum, and it allows Achilles to win the race. This paradox, seemingly so simple, opens the door to a profound truth. Our intuition about something as basic as moving from point A to point B can be deeply flawed when we don't understand the true nature of space and time. But our journey through the paradoxes of the ancient world doesn't end with a race. Zeno had another trick up his sleeve, one that hits even closer to home. Let's call it the dichotomy paradox, or the paradox of cutting in two. Imagine you decide to walk to the park. Simple, right? But Zeno says, to get to the park, you must first get halfway to the park. That seems reasonable. But before you can get halfway to the park, you must first get halfway to the halfway point. So, you must cover a quarter of the total distance. And before you can cover a quarter, you must cover an eighth. And before the eighth, a 16th, and so on, backwards and backwards, dividing the journey into an infinite number of smaller journeys that you must complete before you can even take the first step. This is the reverse of Achilles' problem. There, the infinite division happened in front of him, preventing him from finishing. Here, the infinite division happens behind him, preventing him from even starting. If every journey is composed of an infinite number of smaller journeys, and it takes a finite amount of time to even conceptualize or initiate movement for each one, then how does motion ever begin? It seems like you would be trapped in an infinite regression, forever preparing to start walking, but never actually moving. The resolution, again, lies in the nature of our physical universe. Time and space are not separate, discrete things we experience in little chunks. They are a continuum. The act of movement is a continuous process, not a stuttering sequence of frozen snapshots. Our brains might break it down into steps to understand it, but the universe doesn't operate that way. Just as with Achilles, the infinite series of steps takes a finite amount of time. The sum of an infinite number of increasingly small time intervals is still a finite time. The first step, the one that seems so impossible to initiate, already encompasses all those infinite half-distances within the smooth, continuous flow of motion. Zeno's paradoxes were a powerful reminder that logic alone, divorced from physical observation, can lead us astray. They showed that our common sense notions of space and time were inadequate. It would take over 2,000 years for a new set of paradoxes, born from a new and revolutionary understanding of the universe, to shake the foundations of physics once again. This time, the stage was set not by a philosopher, but by a patent clerk named Albert Einstein. The dawn of the 20th century brought with it a revolution. Albert Einstein, with his theories of relativity, completely overhauled our concepts of space and time. He showed us that they were not absolute and universal, but relative and interwoven into a single fabric, space-time. And with this new, breathtaking picture of the cosmos came a new set of paradoxes that seemed to defy all common sense. The most famous of these is the twin paradox. Let's meet our characters, Al and Bert. They are identical twins, so alike they're practically the same person. Now, Al is a bit of a homebody. He loves his life on Earth, tending to his garden and enjoying the steady rhythm of the seasons. Bert, however, is an adventurer. He dreams of the stars. So Bert hops into a state-of-the-art spaceship, one that can travel at a significant fraction of the speed of light. Let's say 90% of light speed. With a wave, Bert zooms off into the cosmos, headed for a distant star. Now, according to Einstein's special theory of relativity, the faster you move through space, the slower you move through time. This is a real physical effect called time dilation. It's not an illusion. Clocks literally tick slower from the perspective of a stationary observer. So, from Al's perspective, watching Bert's ship speed away, Bert's clocks, his wristwatch, his heartbeat, his every biological process are all running slow. Bert is aging more slowly. After a few years of exploring his destination, Bert turns his ship around and comes back home at the same incredible speed. From Al's point of view, Bert's slow-motion life continues all the way back. When Bert finally lands on Earth and the twins reunite, they get a shock. Al, the homebody, is an old man. His back aches, his hair is gray, but Bert, the traveler, is still young. He looks only a few years older than the day he left. The identical twins are no longer identical. One is significantly younger than the other. This is already strange enough, but here's where the paradox part comes in. A critic might say, hold on a minute, relativity says that all motion is relative. From Bert's perspective, he is the one who is stationary. It's Al, along with the whole Earth, that zooms away from him at 90% the speed of light, and then turns around and comes back. So, from Bert's point of view, shouldn't Al be the one aging slowly? Shouldn't Al be the younger twin when they reunite? This is the core of the paradox. Both points of view seem equally valid, yet they lead to a logical contradiction. They can't both be younger than the other. So, what's the resolution? The key is that the two situations are not symmetrical. Al stays in a single, unchanging reference frame, the inertial frame of the Earth. Bert, however, does not. To turn around and come home, Bert's spaceship has to accelerate. It has to slow down, reverse direction, and speed up again. Acceleration is absolute. Bert feels a force during this maneuver. He's pushed back into his seat. Al feels nothing. This break in symmetry resolves the paradox. The laws of special relativity, which predict time dilation, are formulated for inertial, non-accelerating frames. Bert's frame is non-inertial during the turnaround, so he cannot simply apply the same simple time dilation formula from his point of view. A full, careful calculation that accounts for Bert's acceleration, or more elegantly, a geometric analysis of his path through space-time, confirms the result. Bert, the traveling twin, is indeed the one who ends up younger. This isn't just a thought experiment, by the way. We have direct experimental proof. We've put atomic clocks on airplanes and flown them around the world. When they land, they are ever so slightly behind identical clocks that stayed on the ground. The effect is tiny, but it's there. The GPS system in your phone or your car relies on satellites that have to constantly correct for this relativistic time dilation. If they didn't, your navigation would be off by kilometers within minutes. So, the twin paradox is not just a quirky idea, it's a fundamental feature of our universe, built into the very fabric of reality and essential for our modern technology. It shows us that time is not a universal metronome ticking away at the same rate for everyone. It's a personal experience, a path-dependent journey through the four-dimensional landscape of space-time. As if the twisting of time wasn't strange enough, the early 20th century had another revolution in store, one that would challenge our understanding of reality at its most fundamental level. This is the world of quantum mechanics, the physics of the very small. And if you thought relativity was weird, wait until you meet our next character. A cat who has become the poster kitten for quantum confusion. I'm talking, of course, about Schrödinger's cat. The scene was set by the physicist Erwin Schrödinger in 1935. He was deeply troubled by the implications of the new quantum theory that was being developed by him, Niels Bohr, Werner Heisenberg, and others. The theory worked spectacularly well at predicting the behavior of atoms and particles, but its interpretation was, and in many ways still is, profoundly strange. At the heart of it was the concept of superposition. A tiny particle, like an electron, doesn't have to be in one definite state. Before you measure it, it can be in a blend or superposition of all its possible states. For example, it can be in a superposition of being here and there at the same time. Schrödinger found this idea absurd when applied to the everyday world. To illustrate his unease, he devised a macabre thought experiment. Imagine a sealed steel box. Inside this box, we place a single radioactive atom. This atom is so unstable that within 1 hour, there is a precise 50% chance it will decay and a 50% chance it will not. We also place a Geiger counter next to it, hooked up to a hammer. The hammer is positioned above a small glass vial containing a deadly poison gas. And in this box, we also place a live, healthy, and undoubtedly very confused cat. Now we close the box and wait for 1 hour. According to the Copenhagen interpretation of quantum mechanics, the standard view at the time, the radioactive atom enters a superposition. It is not decayed or not decayed. It is in a fuzzy, undefined state of being both decayed and not decayed at the same time. But this atom is linked to the Geiger counter, which is linked to the hammer, which is linked to the vial of poison, which is linked to the cat. So, if the atom is in a superposition, then the entire system must be. The Geiger counter is in a superposition of having triggered and not having triggered. The hammer is in a superposition of having smashed and not having smashed. The vial is in a superposition of being broken and being intact. And therefore, the cat, the poor creature, must be in a superposition of being dead and alive. It's not that we don't know if the cat is dead or alive. According to this interpretation, the cat is genuinely, physically, in both states simultaneously. It is a ghostly blend of a living cat and a dead cat, a zombie cat of sorts, until the moment we open the box and look inside. The act of observation, of measurement, forces the entire system to collapse into one definite state. We find either a purring cat or a deceased one. This is the paradox. The rules of the quantum world, when scaled up to our everyday level, lead to a conclusion that seems utterly ridiculous. A cat cannot be both dead and alive. That violates everything we know about reality. So what is the resolution? Physicists and philosophers have been debating this for nearly a century. Schrödinger himself proposed the experiment to show how silly he thought the standard interpretation was. So how do we get out of this box? One prominent interpretation is the many worlds interpretation. It says that there is no collapse. When the box is opened, the universe itself splits. In one universe, you open the box and find a live cat, and the atom did not decay. In another, equally real universe, you open the box and find a dead cat, and the atom did decay. Both outcomes happen, but they happen in separate, branching realities. So the cat is always both dead and alive, but never in the same universe. Another view is that superposition simply cannot exist for large, complex objects like cats. A process called decoherence argues that the cat is constantly interacting with its environment, the air molecules, the photons of light, the box itself. These countless interactions instantly collapse the superposition, making it seem as if the cat was in one definite state all along. The transition from the quantum to the classical world is not about size, but about isolation. A cat is far too leaky and connected to its environment to maintain a quantum state. The paradox of Schrödinger's cat has never been fully, universally resolved. It remains one of the most vibrant and contentious areas in the foundations of physics. It forces us to ask, what is the role of the observer? What does it mean to measure something? And where is the dividing line between the fuzzy quantum world and the definite classical world we experience? The cat in the box is more than a punchline. It is a profound question about the nature of reality itself. But the quantum world had more surprises in store, and another paradox that even Einstein found so disturbing, he called it spooky action at a distance. This is the EPR paradox, named after its creators, Einstein, Podolsky, and Rosen. Let's set the stage. One of the key features of quantum mechanics is entanglement. It's a phenomenon where two particles are created or interact in such a way that their fates become linked. They form a single, unified quantum system, even if they are then separated by a vast distance, across a room, or even across the galaxy. Imagine we have a special machine that spits out two entangled electrons. We know that electrons have a property called spin. It's not like a spinning top, but more of an intrinsic magnetic orientation. For our purposes, let's just say an electron's spin can be either up or down. Now, our entangled pair is created in such a way that their spins are correlated. The total spin of the system must be zero. This means if one electron is up, the other must be down, and vice versa. But here's the quantum weirdness. Before we measure them, neither electron has a definite spin. Each is in a superposition of up and down. They are a connected, fuzzy cloud of possibilities. Now, we take these two electrons and we send them flying in opposite directions. We take one, let's call it electron A, to a lab in New York. We take its partner, electron B, to a lab in Tokyo. A physicist in New York decides to measure the spin of electron A. At the moment she does this, the superposition collapses. She gets a definite result, say, spin up. And here's the spooky part. At that exact instant, electron B in Tokyo, no matter how far away, must instantly collapse into the opposite state, spin down. It seems that the measurement in New York has determined the state of the particle in Tokyo, faster than the speed of light. This is the EPR paradox. Einstein hated this. It seemed to violate his theory of special relativity, which states that no information or influence can travel faster than light. How could electron B know what happened to electron A instantaneously? He argued that this spooky action meant that quantum mechanics was an incomplete theory. He believed there must be hidden variables, some unknown local properties of the particles that determine their behavior from the moment they are created, and there is no need for any faster-than-light communication. The particles, in his view, were always destined to be up and down. We just didn't know which was which until we looked. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised a theoretical test, now known as Bell's theorem, that could distinguish between Einstein's local hidden variables and the spooky quantum entanglement. Decades later, experiments were performed, and the results were clear and decisive. They ruled out local hidden variables. The universe voted for spookiness. When two particles are entangled, measuring one does instantly affect the other, no matter the distance. But before you get too excited, there's a crucial catch. This instantaneous change cannot be used to send information faster than light. The physicist in Tokyo just sees a random result when she measures her electron. She has no way of knowing if her result was random on its own, or if it was forced by a measurement in New York. She only sees the correlation when she later gets on the phone with her colleague in New York and compares notes. So, special relativity is saved. No useful information is transmitted faster than light. But our view of reality is forever altered. The universe, at its heart, is non-local. Things that seem separate and distant can be intimately, instantly connected in a way that defies our classical intuition. The EPR paradox shows us that the fabric of reality is woven with threads of entanglement, connecting the cosmos in a hidden quantum web. Our journey now takes us from the intimate connections of the quantum world to the vast, cold expanse of the cosmos. We look up at the night sky, a familiar sight of darkness punctuated by points of light. It seems so natural, so obvious. But in the 19th century, the astronomer Heinrich Wilhelm Olbers asked a simple question that led to a profound cosmological paradox. Why is the night sky dark? Think about it. If the universe is infinite, static, and filled with a roughly uniform distribution of stars, then in every single direction you look, your line of sight should eventually land on the surface of a star. It would be like standing in an infinite forest. Wherever you look, you see a tree trunk. Similarly, in an infinite universe, wherever you look in the night sky, you should see a star. The entire night sky should be as bright as the surface of the sun. Every bit of the sky should be filled with blinding stellar light. But it isn't. It's dark. This is Olbers's paradox. This is not a trivial question. It haunted astronomers for a long time. What could be wrong with the assumptions? Maybe the universe isn't infinite. Maybe the stars aren't eternal. The resolution to this paradox, as we now understand, is one of the cornerstones of modern cosmology. It tells a dramatic story about the history of our universe. There are several key pieces to the solution. First, and most importantly, the universe is not static. It is expanding. This expansion, discovered by Edwin Hubble, has a crucial effect on the light from distant stars and galaxies. The light waves get stretched out as they travel through the expanding space. This shifts them to longer, redder wavelengths, a phenomenon known as redshift. For very distant galaxies, this redshift is so extreme that their visible light is shifted into the infrared, or even radio part of the spectrum, far beyond what our eyes can see. This effect robs the light of its energy, making distant galaxies dimmer and redder than they otherwise would be. Second, the universe is not infinitely old. It had a beginning, the Big Bang, about 13.8 billion years ago. Because the universe has a finite age, there is a limit to how far we can see. This is called the observable universe. We cannot see light from stars that are so far away that their light hasn't had time to reach us in the 13.8 billion years since the cosmos began. The universe could be infinite in size, but we can only observe a finite part of it. This limits the total number of stars that can contribute to the light in our sky. Third, stars themselves are not eternal. They are born, they live, and they die. They have a finite lifetime and a finite supply of fuel. So there hasn't been enough time for an infinite number of stars to have shone in the history of the cosmos. When you combine these factors, the finite age of the universe, the expansion and redshifting of light, and the finite lifetimes of stars, the paradox resolves. The number of stars we can see is finite, and the light from the most distant ones is too faint and too redshifted to fill the sky with visible light. The darkness of the night sky is not just an absence. It is a message. It is direct evidence that our universe is dynamic, evolving, and had a definite beginning. It is one of the most profound observations we can make with the naked eye, pointing directly to the grand cosmic story of the Big Bang. As we ponder the vast, expanding cosmos, a question naturally arises. With hundreds of billions of stars in our galaxy, and many of those stars likely hosting planets, it seems statistically inevitable that life, even intelligent life, should have arisen elsewhere. The numbers are staggering. And yet when we listen, when we look, we find nothing but silence. This contradiction is known as the Fermi Paradox, and it was famously captured by the physicist Enrico Fermi during a casual lunch conversation in 1950 with a simple, devastating question: where is everybody? The logic seems airtight. Let's break it down using what's known as the Drake equation, a way to estimate the number of communicative civilizations. There are an estimated 100 to 400 billion stars in our Milky Way galaxy. A significant fraction of these are thought to have planets. Many of those planets will be in the habitable zone, where temperatures could allow for liquid water. On some of those, life emerges. On some of those, life evolves intelligence. And some of those intelligent civilizations develop technology and the desire to communicate or travel. Even if the probability at each step is very, very small, the sheer number of stars should yield a large number of alien civilizations. Some estimates suggest there should be thousands or even millions of civilizations in our galaxy alone. Given that our galaxy is over 13 billion years old, and that it would only take a few million years for an advanced civilization to colonize large portions of it using self-replicating probes or slow generation ships. The galaxy should be teeming with life. It should be a bustling interstellar metropolis. We should see evidence of enormous engineering projects, like Dyson spheres harvesting the energy of stars. Our radio telescopes should be picking up a cacophony of alien signals. The silence is deafening. So, where are they? This is the Fermi Paradox, the contradiction between the high probability of extraterrestrial intelligence and the utter lack of evidence for it. Over the decades, a huge number of potential resolutions have been proposed, ranging from the hopeful to the terrifying. One class of solutions suggests that intelligent life is extraordinarily rare. Perhaps the emergence of life itself is a fantastically unlikely fluke. Or maybe the step from simple life to complex, multicellular life is the great filter. Another possibility is that intelligence itself is not a stable trait. Maybe all advanced civilizations eventually destroy themselves through nuclear war, climate change, or a technology we haven't yet imagined. The great filter is a hypothesized event or barrier that prevents life from progressing to the stage of interstellar colonization, and we may have already passed it, or we may still have it ahead of us, which is a frightening thought. Other solutions are less grim. Perhaps space is just too big, and the timescales are too vast. The periods when civilizations are communicative might not overlap. We might be like islands in an ocean, separated by millennia and light years, briefly sending out messages that get lost in the cosmic noise. Or perhaps advanced civilizations are out there, but they have no interest in colonizing or communicating. They might be in forms of existence we can't even conceive of, living in virtual realities or as post-biological intelligences, making them invisible to our current methods of detection. Another intriguing idea is the zoo hypothesis, or the planetarium hypothesis. It suggests that they are aware of us, but are deliberately avoiding contact, perhaps to allow us to develop naturally, or to observe us like animals in a cosmic wildlife preserve. Or maybe our entire perception of the universe is a simulation, and the programmers have simply not rendered any other civilizations. The Fermi Paradox forces us to confront our place in the cosmos. Are we a miracle? A fluke? A warning? Or Or are we just one voice in a chorus that we haven't yet learned how to hear? The silence of the universe might be telling us something profound about the nature of life, intelligence, and the challenges of survival on a cosmic scale. Our final destination on this tour of paradoxes takes us to the most extreme objects in the universe, black holes. These are regions of space-time where gravity is so intense that nothing, not even light, can escape. For a long time, they were considered the ultimate cosmic dead ends. But in the 1970s, the legendary physicist Stephen Hawking made a shocking discovery that led to a paradox which has defined fundamental physics for the last 50 years. This is the black hole information paradox. Let's set the stage with Hawking's discovery. He realized that black holes are not completely black. Due to weird quantum effects happening just outside the event horizon, the point of no return, black holes can actually emit radiation. Pairs of virtual particles constantly pop in and out of existence everywhere in space, as allowed by quantum mechanics. Normally, they annihilate each other almost instantly. But if this happens right at the event horizon, one particle can fall into the black hole while its partner escapes into space. The escaped particle carries away energy, and to conserve energy, the black hole itself loses a tiny bit of mass. This stream of escaping particles is known as Hawking radiation. Here's the problem. Hawking calculated that this radiation is purely thermal. It's random, like the heat radiating from a stove. It carries no information about what fell into the black hole. If you throw a 100-kilogram astronaut into a black hole, the hole's mass increases by 100 kilograms. Later, as it emits Hawking radiation and evaporates, it radiates the equivalent of 100 kilograms of mass back into the universe. But that radiation is completely featureless. It tells you nothing about whether the original object was an astronaut, a lump of lead, or a collection of encyclopedias. All the detailed, unique information about what fell in, the DNA of the astronaut, the atomic structure of the lead, the words in the encyclopedia, seems to be irretrievably lost. This is a catastrophe for physics. Quantum mechanics is built on the principle of unitarity, which states that information is never destroyed. It can be scrambled, but never lost. You should, in principle, be able to run the clock backwards and reconstruct the initial state. Hawking's calculations suggested that black holes violate this most sacred principle of quantum theory. This set up a conflict, a paradox between general relativity, which describes the black hole's gravity, and quantum mechanics. Hawking himself initially believed that information was truly lost, which would have required a radical rewrite of quantum physics. For decades, this was the state of play. But recently, there has been a monumental breakthrough. In a series of calculations over the past few years, physicists have come tantalizingly close to resolving the paradox. The new answer, emerging from complex calculations involving the holographic principle and quantum gravity, is that the information does escape. The key insight involves something called the page time, named after physicist Don Page. He realized that if information is to be preserved, the entanglement between the black hole and the Hawking radiation it emits must follow a specific pattern, now called the Page curve. Initially, as the black hole evaporates, the entanglement entropy grows. But roughly halfway through the black hole's life, this trend must reverse. The entanglement must decrease, eventually hitting zero when the black hole completely evaporates, meaning all the information has been returned to the universe. The latest research shows that this is exactly what happens. The information gets out, not in a dramatic burst, but subtly encoded in the correlations between the Hawking radiation particles over the entire lifetime of the black hole. It's like burning a book. The ashes seem random, but if you could collect every single ash particle and analyze the precise correlations between them with impossible precision, you could, in theory, reconstruct the book. The information was not destroyed. It was hidden in the fine-grained details. How does it get out? The working idea is that the event horizon is not a calm, simple boundary. It is a wildly chaotic place, a quantum firewall of sorts, where the immense gravity scrambles the information of anything that falls in and imprints it onto the outgoing radiation. The revised calculations show that the black hole transforms from a sealed tomb to a highly active, scrambling system. New things that fall in are almost immediately regurgitated in a scrambled form. The resolution of this paradox points to a breathtaking idea. Space-time itself may not be the fundamental fabric of reality. It may be an emergent property of something deeper, perhaps of quantum entanglement itself. The fact that information can escape a black hole suggests that the interior of the black hole is not a separate place, but is somehow encoded on its surface, a concept known as the holographic principle. We are nearing the end of the paradox, and in doing so, we are catching a glimpse of the next great revolution in physics. And so, our journey through the most famous paradoxes in physics comes to a close. We've traveled from the ancient tracks of a tortoise and a hero to the fiery evaporation of a black hole. We've seen cats in boxes and twins aging apart. We've listened to the silent sky and wondered at the silent stars. What have we learned? These paradoxes are not failures of science. They are its engines. They are the signposts that point toward the frontiers of our knowledge. Every single one of them emerged when our trusted models of the world, be they philosophical, Newtonian, or relativistic, ran into a wall of their own making. They are the universe's way of telling us, your picture is good, but it's not complete. Look deeper. Zeno's paradox forced us to confront the nature of infinity and the fabric of space-time. The twin paradox was a direct gateway to understanding the relativistic, flexible nature of time itself. Schrödinger's cat and the EPR paradox ripped open the curtain on the bizarre, non-local, and probabilistic quantum world that underlies our seemingly solid reality. Olbers's paradox pointed us directly to a dynamic, expanding universe with a finite beginning. The Fermi Paradox holds a mirror to ourselves, forcing us to ponder the fragility and rarity of intelligence. And the black hole information paradox is currently our most powerful tool for probing the union of gravity and quantum mechanics, for seeing what lies beyond space and time. Each resolution didn't just solve a puzzle, it expanded our imagination. It gave us a richer, more wondrous, and more humbling view of the cosmos. The story of physics is not a story of filling in blank spots on a map that is already drawn. It is a story of repeatedly discovering that the map is wrong, and that the territory is far stranger and more beautiful than we ever dreamed. So, the next time you find yourself lying awake at night, staring at the ceiling, and a paradoxical thought strikes you, don't push it away. Embrace it. Follow it. That feeling of your brain breaking is the feeling of a frontier being pushed. It is the feeling of understanding, dawning just over the horizon. The universe is out there, and it is within you, waiting to be discovered, one beautiful paradox at a time. And so, as the last of those black hole photons slowly radiate away, carrying their hidden information back into the cosmos, we find ourselves back in the quiet of our own world. I hope that journey through the universe's greatest paradoxes was as relaxing for your mind as it was stimulating. If these ideas of cats in boxes, twin brothers, and silent dark skies help you unwind or sparked a sense of wonder, it would mean the world to me if you'd subscribe to Hafee Sleep. We're just getting started exploring the deepest mysteries of the universe, and I'd love for you to be here for the next journey. If you enjoyed this deep dive, please do give the video a thumbs up as well. It's a small signal that helps me know what kind of content helps you all relax and explore the most. Now, I am genuinely curious to hear your thoughts. After all of that, which paradox stuck with you the most? Was it the eerie silence of Fermi's universe, the spooky connection of entangled particles, or the mind-bending fate of Schrödinger's cat? Let me know down in the comments which one you'll be thinking about as you drift off tonight. And if you feel like sharing, let me know where you're watching from once more. It's always wonderful to see our community of sleepy thinkers gathered from every corner of the globe. Thank you so much for spending your time here, for letting your curiosity wander into these strange and beautiful corners of physics. From all of us here at Hafee Sleep, I wish you peaceful thoughts, fascinating dreams, and a restful night. Whatever time it is for you, wherever you are, sleep well, and we'll see you in the next one.